Welcome to today's deep dive. So, if you had a slice of bacon for breakfast this morning, you probably weren't thinking about chemical warfare.
No, definitely not.
Right.
Yeah.
But it was, like, quite literally designed as a weapon. And, I mean, if you walk into any kitchen today, there's this low, constant hum that we just completely ignore.
Oh, the refrigerator.
Exactly, the refrigerator.
Mm.
We trust that white box implicitly. You buy a steak, you toss it in there, and you just expect it to stay fresh.
Yeah, we really take it for granted.
We do. It's this modern luxury, a comfort we've only really had for, the last 100 to 150 years.
Roughly, yeah.
But if you rewind the clock, before the invention of Freon and modern compressors, humanity faced a massive existential problem. Like, imagine you've just successfully hunted a large animal in late autumn. You've got hundreds of pounds of protein.
Right.
How do you keep that meat from rotting before the spring thaw without a single volt of electricity? Okay, let's unpack this, because what we think of as cooking was actually an ancient survival tactic.
Yeah, we suffer from a really big modern culinary blind spot. We look at a kitchen today as a place to assemble meals or, explore fun flavors.
Right, like a hobby.
Exactly. But for the vast majority of human history, the kitchen was not a place of convenience. It wasn't art. It was a literal food science laboratory. And the stakes were, well, life and death.
Wow.
Your survival through a brutal winter depended entirely on your mastery of biology and chemistry. Now, obviously, our ancestors didn't have the scientific vocabulary for those disciplines.
Sure, they weren't wearing lab coats.
Right, but they understood the physical mechanics of them perfectly. The kitchen has always been the site of this ongoing, high-stakes chess game played against an invisible army of microbes.
That's such a crazy way to think about it.
It is, and every piece of charcuterie, every strip of jerky, every slice of salami we casually snack on today, all of that is a monument to that ancient struggle for survival.
And that is exactly our mission for this deep dive. I want to look at this microscopic chess game. We need to look at what we think of today as, cuisine, and re-examine it for what it truly was, a desperate, brilliant survival tactic.
Absolutely.
But before we get into the specific weapons and tactics our ancestors engineered, we have to define the enemy. Like, we use the word spoilage all the time.
Yeah, we say meat goes bad.
Right. As if it's just this passive natural degradation, like a rock weathering in the rain or something. But meat doesn't just magically spoil on its own, does it?
No, not at all. Spoilage is actually an incredibly active, violent biological process. It is a feast.
A feast. Okay.
Yeah, when an animal dies, its immune system stops functioning, which immediately opens the gates for microorganisms.
So we're talking about bacteria, molds, that kind of thing.
Exactly, bacteria, molds, and naturally occurring enzymes. They move in and they begin to break down and consume the complex proteins and fats in the meat. They are literally eating your food before you can.
Okay, that's slightly terrifying.
It's nature. But this microscopic enemy has a crucial vulnerability. To survive, to metabolize that meat, and to multiply, these organisms absolutely require 3 specific environmental conditions.
Okay, so they need water, right?
Mhm.
They need a relatively warm temperature, and they need oxygen.
Yes. Those are the rigid demands of almost all pathogenic bacteria. If they have a moist environment, a temperature between roughly 40 and 140 degrees Fahrenheit, and access to the air, they don't just survive, they thrive.
They just take over.
They multiply exponentially, and your meat becomes toxic and rotten in a matter of days.
So it's essentially a biological fire.
That's a great way to put it.
Like, think about the mechanics of a campfire.
Yeah.
If you want a fire to burn, you need fuel, you need heat, and you need oxygen.
Right.
If you take away the wood, or you dump a bucket of water on the coals to kill the heat, or you throw a heavy fire blanket over it to cut the oxygen, the fire dies. It physically cannot exist. So, if the formula for bacterial life is that mathematically simple water, warmth, oxygen, stirable, what was the very first tactic our ancestors stumbled upon to put out that biological fire?
Well, if we connect this to the bigger picture, the entire history of food preservation is simply humanity learning how to systematically eliminate just one of those 3 life-giving pillars, and the most accessible pillar for early humans to attack was water.
So just dry it out.
You simply deprive the enemy of moisture. This brings us to desiccation, or drying, which is the absolute oldest preservation method in human history.
Makes sense.
The biochemical concept is beautifully simple. Bacteria are single-celled organisms, and like all life on Earth, they rely on water to facilitate the chemical reactions inside their cells.
Right.
If there is no ambient water in the meat, the bacteria physically cannot function. Their cellular machinery just grinds to a halt. They desiccate and die.
But the physical reality of doing that has to be complicated, right? Like you can't just leave a whole leg of a deer out in the sun and hope for the best.
No, definitely not.
Because the intense heat might dry out the outer quarter inch of the muscle, like creating a hard crust. But the interior would remain completely moist.
Yes, you'd just be creating a warm, wet, protective incubator for bacteria on the inside. The meat would rot from the bone outward.
Gross. So how do they actually do it?
The geometry of the meat is the single most important factor. The ancient technique discovered through trial and error over millennia relies on maximizing the surface area to volume ratio.
Okay, so you have to cut it small.
The meat must be sliced into incredibly thin strips. Then you expose those thin strips to the sun, or more importantly, to the wind.
Wait, the wind is more important than the sun.
Oh, absolutely.
Yeah.
Continuous airflow is far more critical than direct heat. The wind acts as a physical sponge, constantly pulling moisture away from the surface of the meat through evaporation.
Yeah.
Meanwhile, capillary action slowly draws the deep moisture from the center of the thin strip to the surface.
Wow. Which explains why this specific tactic is universal across completely disconnected cultures. Like, Native American tribes developed what we now call jerky by hanging thin strips of venison or buffalo on wooden racks in the wind.
Yes, exactly.
And then in South Africa, indigenous populations and later European settlers developed biltong.
Right.
And if you look at the early nomadic tribes of Central Asia, they were making the early precursors to pasteurma. It was just wind, sun, and deeply understood geometry.
And when executed perfectly, that dried meat can last for months, sometimes even years, completely at room temperature. It becomes a dense, incredibly lightweight, nutrient-packed ration.
That's wild.
Think about those Central Asian nomads. They practically lived on horseback, traveling thousands of miles across the steppes. Their entire civilization's mobility relied on dried meat stored in their saddlebags. It provided the caloric density necessary for empire building.
Okay, so drying is incredibly effective.
Right.
But our ancestors didn't stop at just relying on the weather, right? They found a biological cheat code to accelerate the process: salt.
Yes, salt, the ultimate enemy of bacteria.
Now, when I salt a steak today, it draws a little moisture to the surface and seasons the meat. But to actually desiccate a massive piece of pork for long-term storage, they couldn't just use a light sprinkle, right? How do they ensure the deep tissue cured thoroughly before the bacteria took over?
It required an absolute burial.
Wait, a burial?
Yes, the ancient method of salt curing involves encasing the meat in thick, heavy layers of coarse salt. Every square millimeter of the meat's surface must be in direct, pressurized contact with the salt, with absolutely no air gaps.
So it's completely submerged in salt.
Completely. And what's fascinating here is how salting works on a cellular level. It doesn't just passively absorb moisture like a sponge. Through the physical law of osmosis, nature seeks equilibrium.
Right.
Because the concentration of salt on the outside of the meat is so incredibly high, it creates an extreme osmotic pressure that actively, forcefully draws the water out of the meat's cells.
And I'm guessing it does the exact same thing to the bacteria, right?
Oh, it is devastating to the bacteria. If a microbe lands on heavily salted meat, that same extreme osmotic pressure literally sucks the water straight through the bacterium cell wall.
Oh, man.
The microbe's cytoplasm is drained, its cell membrane collapses, and it is crushed from the inside out. It's an incredibly hostile environment.
The historical impact of this microscopic violence just cannot be overstated. I mean, we see the culinary remnants today in modern pasteurma, salt cod, and prosciutto, which, is really just a pig's leg and sea salt, aged in a climate-controlled room until it's perfectly safe to eat raw.
Exactly.
But historically, mastering salt logistics changed the map of the world. Think about the Roman Empire. Roman legions, sometimes marching with 5,000 or 10,000 men, required immense, reliable caloric density.
Yes, they marched across Europe and North Africa, fueled by daily rations of heavily salted pork.
And isn't it true that the word salary comes from salt?
It does. The word salary itself comes from the Latin word for salt because Roman soldiers were often paid in salt or given an allowance to buy it.
That is so cool.
And that technological reliance only accelerated during the age of exploration. When sailors began crossing the Atlantic, they were surviving for months at sea in notoriously damp, humid conditions where simple air drying would instantly fail.
Because it's too wet.
Right. So they relied on massive wooden barrels packed to the brim with wet, salt-cured beef and pork. Without the sheer osmotic power of heavily salted meat, surviving a transoceanic voyage and thus the entire era of global exploration would have been geographically and biologically impossible.
Okay, so what does this all mean? Like, salt and wind are fantastic weapons. If you live in a dry desert or on a coastline where you can evaporate seawater to harvest unlimited salt, you're set.
Yes, you're in a great position.
But what if you don't? What if you live in a wet, damp, rainy climate where the sun can't just bake it dry?
Yeah.
Like, people couldn't just rely on the desert strategy. The air is entirely too humid to wick away moisture, and maybe you don't have access to massive salt mines.
That's a very real problem they faced.
Right. You'd have to abandon the strategy of attacking the water pillar.
Yeah.
You have to pivot to a completely different battlefield, right? Attacking the hospitable environment and the oxygen. So let's talk about chemical warfare. Let's talk about smoke.
Okay, smoke is fascinating. When you go to a modern barbecue restaurant today, smoke is treated purely as an aroma, a flavor profile to enhance a brisket.
Yeah. We just think it tastes good.
Right. But originally, smoke was an active, deadly weapon against microbes. Burning wood releases a highly complex cocktail of chemicals. Smoke contains thousands of volatile compounds, but the most important for preservation are phenolic compounds, formaldehyde, and organic acids.
Formaldehyde. Wow.
Yes. When you expose meat to smoke, you are coating it in an invisible, highly toxic shield.
Okay, wait. We hear the word toxic and usually think it's bad for us too. How does it kill the bacteria without killing the human eating the bacon?
It comes down to concentration and cellular structure. The phenolic compounds in wood smoke actively disrupt bacterial cell membranes. They penetrate the microbe and denature its proteins.
Denature. What does that mean exactly?
Denaturing means the chemical structure of the protein physically unravels. Think of what happens to a clear egg white. When it hits a hot pan, it turns white and solidifies.
Oh.
That same unraveling happens to the critical proteins inside the bacteria, completely shutting down their biological functions. And the organic acids in the smoke also rapidly drop the pH level on the surface of the meat, creating an acidic environment where mold spores physically cannot germinate.
So the traditional smoking process isn't really about cooking the meat through heat at all.
No, not at all. Cold smoking, the most traditional preservation method, intentionally avoids cooking the meat. The meat is hung in a chamber, like a smokehouse or the rafters of a chimney, over a very low, smoldering fire.
Like, how low are we talking?
We're talking about ambient temperatures well below what would actually cook the muscle, sometimes for days or even weeks on end. The smoke slowly penetrates the outer layers of the meat, depositing those phenols and acids deep into the tissue.
Oh, wow.
This is the origin of classic smoked salmon, smoked sausages, and bacon. A heavily smoked piece of meat kept in a relatively cool cellar will outlast fresh meat by months simply because the bacteria are instantly poisoned the moment they try to land on that phenolic barrier.
Okay, so if smoke poisons the battlefield, the other tactic you mentioned was suffocation, a physical blockade, taking away the bacteria's oxygen entirely. Which brings us to one of the most brilliant culinary traditions from the old French kitchen, the confit.
Ah, yes. Confit relies on a deep, intuitive understanding of physics and physical barriers. The process usually begins with waterfowl, like a duck or a goose. The meat is heavily salted to draw out some initial moisture, and then it is submerged entirely in its own rendered fat and cooked at a very, very low temperature for hours.
Now, slow cooking tenderizes the meat by breaking down the tough connective tissues and collagen, sure, but heat alone isn't a long-term preservation strategy. Like, once you take a cooked duck out of the oven and let it cool down, it's just cooked meat. It will actually spoil faster than raw meat because the cellular structure has already been broken down for the bacteria, right?
Exactly. The actual preservation phase of confit happens entirely after the cooking is finished. While the meat and the liquid fat are still boiling hot, meaning the environment's perfectly sterile and all existing microbes have been destroyed, the meat is transferred into a stone crock or a jar.
Okay.
Then, that hot, liquid rendered fat is poured over the top, completely submerging the duck.
And because it's an animal fat, like a saturated fat, it doesn't stay liquid at room temperature like olive oil would.
Exactly the opposite. As the temperature in the room drops, the saturated fat crystallizes and solidifies into a dense, thick, absolutely impenetrable cap. Saturated fats pack together very tightly at a molecular level.
Here's where it gets really interesting. It's like putting the meat inside a greasy spacesuit.
A greasy spacesuit, I like that.
Yeah. It creates a localized vacuum seal. It's a flawless physical barricade. The mold spores and bacteria floating in the air of the cellar can land on top of that solid fat cap all they want, but they cannot swim through solid lard.
No, they can't.
And because the hot fat sterilized everything underneath it before it cooled, there is nothing alive inside the jar. You've completely eliminated the oxygen pillar. The bacteria literally suffocate.
Yes. A traditional duck confit stored in a cool, dark French cellar, completely entombed in that solid fat cap, could safely be eaten 6, sometimes even 12 months later. No ice, no electricity, no chemical preservatives.
That is amazing.
And it's important to note that the specific understanding of fat as an oxygen barrier wasn't limited to Europe. North American indigenous tribes utilized the exact same physical principles to create pemmican.
Oh, right. I've heard of pemmican.
Yeah, they would take dried, pulverized lean game meat, mix it with foraged berries, and then completely encase the mixture in hot rendered suet or tallow. Once that fat cooled and hardened, the pemmican became an incredibly calorie-dense survival ration that could last for years in a leather pouch, purely because the fat locked out the oxygen.
So we have dried the enemy out, we have crushed them with osmotic pressure, we have poisoned them with phenolic smoke, we have suffocated them under rendered fat, we are relentlessly attacking these microbes.
Yeah.
But there is one final method in our source material today, and I think it is the ultimate plot twist in our historical chess game.
It really is.
Because up until this point, our entire culinary strategy has been to create a sterile environment. Kill the bacteria, block the bacteria, starve the bacteria. But the final, most advanced method doesn't fight the bacteria directly. It recruits them.
This raises an important question, though. You are talking about fermentation, which is, without a doubt, the highest level of food science ancient humanity ever achieved. It represents a complete paradigm shift in how we approach preservation.
It's the Trojan horse strategy. Instead of building walls, you let the army inside.
Exactly. Instead of trying to eliminate all microbes, which is nearly impossible to do perfectly outside of a modern laboratory, you selectively introduce specific beneficial bacteria to the raw meat. You essentially seed the battlefield with your own troops before the enemy can even arrive.
Which is wild, because when I think of fermentation, I usually think of like beer or kimchi or sourdough bread. Doing it to raw ground meat feels incredibly dangerous.
It is incredibly dangerous if you don't understand the biochemical levers you're pulling. The primary allies in meat fermentation are lactic acid bacteria. When ancient sausage makers mixed ground meat with specific spices, salts, and sometimes a little bit of sugar or wine, they were intentionally creating the perfect breeding ground for these specific lactic acid bacteria.
Oh, I see. It's like hiring microbial mercenaries. Like, the good bacteria act like bouncers at a club, fiercely protecting the meat by keeping all the bad bacteria out.
Yes. Or you could look at it like terraforming.
Right. You're bringing in an organism designed to aggressively alter the climate of the meat.
Terraforming is the perfect analogy. When these beneficial bacteria are introduced to the meat mixture, they wake up and immediately begin consuming the available sugars. As they metabolize those sugars, they rapidly multiply. But more importantly, their digestive byproduct is profound amounts of lactic acid.
Which fundamentally changes the environment.
It drastically lowers the pH level of the entire sausage. The environment becomes highly acidic. And the pathogenic, harmful bacteria, the ones that cause severe food poisoning like botulism, or the ones that cause putrefaction, they physically cannot survive in a high-acid environment.
It's not just building a wall, it's literally altering the atmosphere of the meat so that the bad bacteria suffocate, the good bacteria aggressively outcompete the harmful ones.
Yeah.
They eat all the available food, they take up all the physical space, and they terraform the terrain to make it intensely toxic to rival organisms. This is the complex science behind highly prized, long-lasting cured meats like traditional Turkish souk, intensely flavored Italian salami, and, the pepperoni on your pizza.
Furthermore, in many of these fermented sausages, like a high-quality salami, you'll notice a powdery white mold growing on the outside of the casing.
Yeah, what is that?
That isn't a mistake. That is usually a specific mold called Penicillium nalgiavens. Sausage makers cultivate that specific white mold because it acts as a secondary biological shield.
Oh, wow.
It aggressively covers the entire outside of the sausage, preventing any harmful, toxic black or green molds from taking root. It also protects the fat inside the sausage from oxidizing and going rancid while the inside ferments.
When you stop and really think about the history of this, it is genuinely mind-blowing. Humanity completely mastered this. They allied with microscopic organisms, they managed specific ambient temperatures in curing caves, they controlled humidity, and they selectively bred bacterial cultures to fiercely protect their food supply. Thousands of years before the invention of the microscope.
It's incredible. They had no concept of cellular biology. They didn't know what a pH scale was. They couldn't see the lactic acid bacteria or the mold spores. Yet, through rigorous observation, deep intuition, and generational knowledge passed down over centuries, they perfected a biochemical process so incredibly complex that modern science is still sequencing the DNA of these microbial ecosystems today.
Unbelievable.
They mapped the entire invisible world of microbiology using nothing but taste, smell, and the brutal binary of survival.
We tend to treat ancient humans like they were unsophisticated, just dragging clubs around. But they were executing high-level, precise biotechnology in clay pots, animal casings, and damp European caves. It forces you to completely redefine what you consider to be technology.
Definitely.
A wooden barrel packed with salt, or a hanging leg of pork being carefully monitored for beneficial mold growth, is a highly advanced technological system. It just runs on biology and chemistry instead of electricity and silicon.
Each of these ancient methods approaches the exact same scientific principle from a radically different angle. Whether it's the wind pulling moisture out, the salt crushing the cells, the phenolic smoke denaturing proteins, the fat blocking the oxygen, or the lactic acid dropping the pH. The goal was always the same.
Disrupting the living conditions of the organisms that want to consume our calories before we do.
Exactly.
So to bring this all together for you listening, the next time you order a pizza loaded with pepperoni, or you have a crispy slice of bacon with your breakfast, or you grab a bag of beef jerky for a long road trip, I want you to look at that food differently. You aren't just eating a quick, highly processed snack. You are literally tasting the physical results of an ancient, high-stakes chess game played against an invisible army of microbes. You are eating the victory condition of our ancestors.
It is the accumulated, hard-won wisdom of human survival distilled down into a single bite of food.
Which leaves us with a final, slightly unsettling thought to mull over. We open this deep dive by talking about that white box humming away in your kitchen.
The modern refrigerator.
Right. It is clean, it is incredibly easy, and to us it's practically magic. You just open the door and put the meat inside. But if our ancestors were able to engineer raw protein to last for months or even years using absolutely nothing but the local weather, salt rocks, the smoldering smoke of a fire, and by negotiating complex treaties with microscopic bacteria, how much of our fundamental human knowledge about food science, biology, and raw, pragmatic survival are we slowly losing simply because we can just plug a cold box into a wall? Think about it. Until next time, thanks for taking this deep dive with us.